Yeah, so first thing is regarding the quiz. See, our plan, we will not have the quiz tomorrow. Yeah, so what we will do is I would like you all to, to work on OJ and get used to it. So towards that, we will put assignment 1 on OJ. And so in tomorrow's session, you should try to submit your assignment 1 using the OJ. You may have to slightly modify your programs to match the input and output formats which the OJ asks for. Since OJ is an automated evaluation system, it it's an automated evaluation system. What happens is, the input and output formats will be fixed. So if your logic is working, you just have to slightly modify your program so that you take the input and output the way it's asked for. Okay, so we will similarly assignment 2 will also be kept on OJ, but first we will solve the we will now all assignments will be on OJ. For tomorrow, you will all try to make an effort to put to upload all your assignment 1 problems on OJ during the lab session tomorrow. No, challenge problems also will be have to do. See, there is no lab for us, no computer programming. We just solve problems. That is the lab for computer programming. So there is nothing specific there. Yeah, you can take time. You can upload even after tomorrow also. And there is one important thing. We discussed about the Pythagorean triplets. Yes or no? How to solve that problem. So what is the challenge problem 2 weeks before? Is it still a challenge problem for you? At that time, it's a challenge, no? But not now, right? So it's no longer a challenge problem. You should be able to solve it. Okay, so you have to submit all your problems. Okay, challenge problems, everything included, you have to submit. That is for assignment 1. And again, deadline, don't worry about deadline. Yeah, so ideally you should try to do it by tomorrow, but if you take a bit more time, it's okay, don't worry. All right. There is no quiz tomorrow. Okay, so you will, no, there is no quiz tomorrow. The assignment will appear on OJ hopefully by tonight or tomorrow. I'm not visible, that's true. I didn't enable my. Okay, so deadline for assignment. When is the quiz? I'm saying, okay, guys, you will not change. I hope you'll change. Same questions. Okay, I think we should start. Okay, I repeat, tomorrow there is no quiz. Number 1, we will have the quiz next week, sometime next week. Okay, number 1, that's number 1. Number 2, assignment 1 will be posted on OJ by tonight. During the tomorrow lab session, if you can submit your assignment on OJ, it's awesome. but you can take a little bit more time, so don't get stressed out. All right, that's number 2. And number 3, yeah, let's start. We should. Uh, so yeah, now let's look at assignment 1. In assignment 1, in the challenge problem, we discussed about just give me a minute. All right, yeah. So in assignment 1, so what did we do for Pythagorean triplets problem? So this is the approach that we followed. We tried the hypotenuse value h is equal to 1, h is equal to 2, so on and so forth, h is equal to I. And for every h, okay, for every h, check, okay, check if h is a hypotenuse. And the approach that we followed there is, so S1 and S2 are sides of the triangle. So the algorithm 1 that we used for checking if H is a hypotenuse is we tried out, S1 less than H, and then yeah, so S2 less than H. For all these possibilities, we checked if S1 square plus S2 square is equal to H square. This is the check. And in terms of the table, so if you see, this is the table. So this is S1, this is S2. So we try different values of, so we go through this table row by row, and that's how we check whether there is a potential sides S1 and S2 which satisfy the constraint, the equation S1 square plus S2 square is equal to H square. This is what we check as we iterate through this table. And so approximately, so the number of iterations that we go through is H square. Are you with me here? Approximately we go through H square. This is an approximation. We are not interested in exactly number, but approximately it is H square. Okay, are you fine with this statement? H minus 1 by 2. Now we try out all the possibilities in this table, and there are roughly H square entries in this table. That's all we are saying. We are just looking at, given a particular potential candidate for hypotenuse, whether it is really a hypotenuse or not, we take H square time, approximately. No, I'm saying approximation. So that's why H minus 1 square, H square, they are approximately the same. Like for example, so like for example, this is, so let's say H minus 1 square divided by H square. This is equal to 1 minus 1 by H square. Yes or no? And what happens limit as h tends to infinity? This term goes out to 0. This is equal to 1. So the difference between h minus 1 square and h square is not really big as we keep increasing the value of h. Does this make sense? Looks like you're all in holiday mode. So is that yes for holiday mode or for that why it's okay to consider h square? Both. Okay, good, good, good. Not in holiday mode. So you should, both is good. Both is good. Yeah. Nice. All right then. So Aman is in between. Huh? How is it in between? Or between holiday mood and this? Okay, tending to holiday mood. Okay, good. So now, and we were not happy about this. Okay, and so only gift I want this time is my code to run. So let test your luck with Santa, Himanshu, and see what happens. There is no problem with algorithm when it works. It is h square. But then we figured out, that if you take ith row and jth column, like I comma jth here and j comma I, we are trying out the same thing 2 times. Okay, checking whether, it's like dumb thing, right? I square plus j square is equal to h square. You are checking j square plus I square is equal to h square, both. It's brute force, we are trying both. Doesn't make sense to try both. So we changed our code, and then after changing the code, and of course, both outcomes will also come. There is a problem. So we changed our code in algorithm. In the second approach, we did this. And when we did this, the way we iterated we iterate the upper triangular matrix. So after this iteration, approximately the running time is h square by 2. This is approximately. Is it okay? Great. So in section A, I thought, no, I have a way to reduce the running time, which didn't quite work, but nevertheless, let's go through it, and we will find the bug in the argument. So the third approach is you try one is so you try for you look for S1, and we say we get we say k is equal to h square minus s1 square, and then check if k is a perfect square. How can we check if k is a perfect square? How can we check if k is a perfect square? Square root is an integer. Okay. So what happens is you have to be careful here. So so one way of so the problem that we get is, okay, the idea here is you try to compute square root of n, and square root of n, yeah, it's square root of n. So there are two things. So there is a way to check it, but there are issues with that approach. So Sai Kiran has a good approach. So, but broadly speaking, so let me first, I think I like Sai Kiran's approach. But let's say before we do that, the problems that we face, when we do, like say, for example, square root of 4, when we do, actually what happens is, the way computation happens is, square root of 4 gets typecasted to 4.0, and then 4 square root of 4.0, 4.0 may not have an exact, this itself may not have an exact representation. In the computer, it may be represented as 3.99999 or even 4. It depends on the number. And it is 2.0, and there are 2.0 may not be exactly be represented. And no, you may have 1.99999 or 2.00001, so on and so forth. So what happens is, so in order to solve this problem, what you do is you kind of round this number. You round this number to an integer, and check if it works. Okay, but the problem is, some of these things, they can go wrong, because it can work in some cases, but we don't know, if you're not careful about it, it wouldn't work in some cases. That means we can falsely conclude something as a perfect square, or it could be a perfect square, and and we may discard it as a not a perfect square. So these things are possible. So what I want you to keep in mind is, in this process, there are two levels of approximation that are happening. Two levels of approximation, two levels. What is the first level of approximation? Approximation due to representation. When you represent an integer, when you do typecasting, some approximation happens. And the second thing that happens is, the computation of square root also introduces some approximation. All right. So there are issues. Okay. Because of that, sometimes I want you to pay attention to the discussion here. This is a very, very important point. Sometimes we may falsely classify, conclude that something is a perfect square, whereas it is not. And it may not be such a big deal. Okay, it may not be such a big deal in this particular case. It may not be such a big deal in this it may not be such a big deal in this particular case. So what do we do? But in some problems, what happens is I have some interesting idea from Shivain, so I will follow it up later. You have to be careful because in the test cases that you did, it looks perfectly fine, but you may encounter some test cases where these approximation errors can have disastrous consequences, like a rocket instead of going up, it may end up nose diving into the ocean. Okay, or on Mars, while the rover is landing, it may land few 100 meters away or a kilometer away, and and you end up landing in a bad place. So you have to be very careful and argue that the representation errors wouldn't cause any problems, that the computation, that the approximations due to computations wouldn't cause you any problems. So please keep this in mind. Please keep this in mind. Okay, are you all with me here, that this particular approach of going to the floating point space, doing computations and moving between integers and floating point numbers, I'm not saying you should not do it, but you have to be careful. Are you all with me here, that you should be cautious here when you are traversing between these two spaces, integer to float or double and float to integer, and computations, the approximations gets introduced, and things can go bad if you are not careful and if you don't know what you are doing. You cannot just rely on trying out on few test cases and say, hey, it worked on the few test cases I worked with. So this is a big thing I want you to know upfront now in your C programming course. Okay, not 10 years later when things went really bad on some project which you are working. So what do we do? So now one approach, so without going to the floating point space, one approach to solve this problem without approximation, without using floating point numbers and all this is so you try, 1 is less than or equal to k, 2 times 2 is less than or equal to k, so on and so forth. And then so finally, if you have at some point you'll hit an I where there are two cases. One case is I star I is actually equal to k, in which you conclude that k is a perfect square. The other case is I star I is greater than k, at which case again we will break. So these are the two cases that you will encounter. Are you fine with these two cases, that as we keep proceeding, that that either I star I is equal to k or I star I is greater than k. These are the two cases. What is an upper bound on I? What is an upper bound on I before this thing happens? Can you give an upper bound on I? Square root of k, square root of h. Can we say I is less than h? I should be less than h because k is approximately h square, right? So we can, the worst case, the highest value of k is h square. So we can kind of say, that an upper bound on I is h. An upper bound on I would be h. So if you see, then what is happening is, in order to check, we are kind of doing an approximate analysis. Okay, bear with me. So we are doing an approximate analysis. And if you see, look at this approach, did we gain anything in this approximate analysis? If we are going till H, what happens is you pick a value of S1 and so this is the outer loop. So this is outer loop. Trying out S1 from 1 to H is outer loop. And then this whole thing is inner loop. Does this make sense? This inner loop and outer loop business. So if you see, the outer loop is going H times and the inner loop is not exactly going H times, but if you do a careful analysis, you will initially I thought you will get a better time complexity, but this may still be approximately H square by 2. Okay, approximately it may be the time complexity of this whole algorithm, it gives H square by 2 approximately. Well, you have to be a bit careful. No, we are not doing time complexity, approximately computing the number of iterations it is going to work. Yeah, you can kind of ignore this H square by 2. You can just think it's okay, H square. Okay. I don't want to do that analysis because that's not the point. But roughly speaking, definitely you may get something like this. Is this okay with you for the time being? Now, approximately the outer loop is going, S1 is going from 1 to H. And in the inner loop, we take K is equal to H square minus S1 square. And we keep trying this, keep checking 1 times 1 is less than K, 2 times 2 is less than K, so on and so forth. I times I is less than K. We are looking at approximate, we will think, in the worst case, the bound of on I, the maximum value of K is H square, right? The maximum value of K is H square. Approximate, okay, not interested in -1 and all. So because of that, you may I may go till H. So this is all approximate computation we are doing. So won't answers repeat in this algorithm? Maybe I didn't think about it. But one thing we can do here is Raven, perhaps, okay, yeah, maybe we have to think about it. One thing we can do, can we do better than this? So we are trying out 1 is less than or equal to K, 2 is less than or equal to K. Can we do better than this? Yeah, so the better thing is I'm trying to look for an algorithmic way to do it. Perhaps a better way to do it is, if you see, let's go from here. So what we are trying to do, pay attention. So we want to see if we want to try for different values of I ranging from 1 to h. Okay, whether I times I is equal to k square. Okay, so find check if there exists I, no, where this I satisfies this condition that I lies between 1 to h, such that such that I square is equal to h square minus s1 square. Okay. So now there is this idea of this binary search. Okay, so what do we do? So in binary search, what we do is we think initially, okay, we can start with I is equal to 1. We start with I is equal to 1. And if I square is less than h square minus s1 square, the next I that we check, what is the next I that we check is, if this is the case, the next I that we check is 2I. If I square is less than, that means no, our estimate of I is smaller than this, so we try 2I. And on the contrary, if I square is equal to h square minus s1 square, we are good. But if it is greater, there are three possibilities. I square is equal to h square minus s1 square, in which we will stop. Or if I square is less than h square minus s1 square, no, we want to, we say 2I. Otherwise, if h square, no, if this is greater than, then we try out on I by 2. Are you with me here? So let's go to a new page and try this. Why am I not getting a new page? Okay. Pay attention here. So what we are trying to do is please pay attention. Okay, so see, what we are trying to do is we started with, we want to, so step 1, so we pick S1, some value of S1 we have, whatever it is, or let me do this one. So what we have is K is equal to h square minus S1 square. Okay, K is equal to h square minus S1 square. Are you with me? And what is the problem? We want to check if K is a perfect square. Okay, so we want to know, so there is an I which lies in the interval, there is an I which lies in the interval 1 to h. Okay, we want to check if there exists an I in the interval such that I square is equal to h square minus s1 square. This is the question. Are you all with me here? And I would like you to, so this is our initial estimate. This is our initial estimate of the interval. So what we do is, there are multiple ways of trying to solve this problem. So one way of solving this problem, in this particular case, let's start with I is equal to so we check, we start with So we check if I is equal to, now is we start with I, this is what we do. We start with I and we check if I square is equal to, we compare I square with, no, so compare, let me write it this way. Compare I square with H square minus S1 square. So the easiest case, no, equal to, if they are equal, then we are done, right? This is the easiest case if you are done. Yes or no? This case, if I square is equal to H square minus S1 square, we are good. The second possibility, the possibility is I square is less than H square minus S1 square. Okay. If I square is less than S1 square, then what we try to do is we double I and we check. Okay, this is one possibility. The other possibility is I square is greater than H square minus S1 square. Okay, this is other possibility. Okay, so if this is the line, so we started, so this is, yeah, so this is 1 and this is H. Okay, so if, so now what happens is, let's say somewhere if the current value of I is here and the current value of this is I is here, and if I square is less than H square minus S1 square, then if at all such an I exists, whether it will lie in the left side or in the right side. It will be in the right side, right? So we want to focus our attention. We want to focus our attention on, we want to shrink our interval and we want to focus our attention on this part, on the right side part. That is, on the contrary, if I square is greater than H square minus S1 square, then no, we will we have to focus on the left part. So here, so if this is the case, then no, our estimate, no, this this indicates that the potential, this is the search area, and no, this, if this is the case, we should look for this in this space. Let's not worry about repetitions. We are trying to find an interesting algorithm, and okay. So what we do is, what if 2i is greater than h? Okay, we will see. Let's try to figure this out. But broadly speaking, what we want to do is at every time, we would like to kind of, look for, or rather, let's do one thing. Let me put it in a different way. Instead of starting the search space, starting with I is equal to 1, it is better to start with I is equal to midpoint. Okay, maybe H plus 1 by 2. So what we do is, let's draw a binary tree here. Okay, so we start with initial value of I is equal to H plus 1 by 2, and we check this condition. So what happens is there are two possibilities. This is I square is less than, whatever I square is less than this, and I square is greater than this. So if I square is less than whatever this H, Yeah, I square is less than k and I square is greater than k. Okay. So if I square is less than k, then what is the interval we should be focusing on? Can you tell me? If we start with I is equal to, so let me redraw this picture for you. Okay, I think I kind of confused you a bit. I will erase this picture and compare I square with, okay, let's have this. Okay, let's restart so that the particular starting point I said, that will be I is equal to 1. You can do it, but it is painful. But let's start with this. Okay, we start with I is equal to h plus 1 by 2 or some range, some mid. We start with I is equal to mid. Are you with me here? Okay, so now you check. So you compare I square with k. Okay, you compare I square with k. I square is greater than k. So there are, so if at any point, if I square is equal to k, then we are done. I square is equal to k. No, we are done. That is, we figured out that k is a perfect square. Are you with me here? That if you find an I such that I square is equal to k, we are done. Okay, that is. But on the contrary, if I square is greater than k, then so what is the thing? Then we should be looking at the interval. What is the interval that we should be looking at? We should be looking at the left side. Okay, we should be looking at the left side, 1 to I. This is the interval we should be searching for. On the other side, we should be, if I square is, we should be looking at the interval I plus 1 to h. Are you with me here? If I square is greater than k, yes and no. Are you all with me? So we started with an estimate of I. If it's a, what is the estimate? We took the middle point as the estimate. And if if you are lucky and if our estimate is right, we conclude. Are you with me on that? We start with an initial estimate of I, and if you are lucky, we are done. Okay. If we overestimate, what should we do? If we overestimate, what should we do? If we overestimate, then no, we should go to the lower part, left part. Yes or no? 1 to I. If we underestimate, what should we do? The right part. Are you all happy with this one? Does the picture make sense? Whatever the picture that you are seeing here. Now we have to repeat the same again. Okay. You have to keep repeating the same again here. Okay. So this is, we learn. So now you are getting introduced to a new idea of recursion, but we have to repeat the same again. We have to keep, every time you take a step, what will be the size of the interval compared to its parent size? It becomes half. So within how many steps the interval becomes equal to 1? It's very small, 1 or 2 size. Within log steps, log of h. So if you look at the whole tree, in log h steps you will compress, you will finish your search. Does this make sense? Are you all with me? Log h to the base 2, or every time it gets half, na? Log h is a worst case scenario. Yeah, that's true. Every time the interval keeps on decreasing. Okay, initially the length of the, so at this level the length of the interval is h, because our initial estimate is it will lie anywhere between 1 to h. The length of the interval is h. At the second level, the length of the interval is h by 2 after one iteration. After the next iteration, the length of the interval is h by 2 square, so on and so forth. Finally, when it becomes h by 2 power k, when the size of the interval is equal to 1 or 2 very small number, you will stop. So h is equal to 2 power k. So k is equal to log h to the base 2. Does this make sense? Are you all with me? That, and we are not exploring the whole tree. We are taking only one particular path in the tree. Good. So now the hypotenuse, we will check whether something is a perfect square, this condition, using log h time. Okay, using log h to the base 2 time. So overall time complexity becomes h times log h to the base 2. Yes or no? Because here, if you now, I'm switching to a blue color. So the outer loop is giving contributing h, and the inner loop we are able to do in log h to the base 2. For the time being, we can just think of the time complexity as iterations. Is this okay? This h is coming from outer loop. This h is coming from outer loop. This is coming from inner loop. Are you fine with this? Are you all okay with this argument? Happy? New technique? Time complexity is, for the time being, you just think of the number of iterations, the amount of work. Think of it like this, Kriti. Like, for example, your mother gives you 100, a list of 100 items to buy from the grocery store. So there are two possibilities for you. You go to grocery store and get all the items once, or every item you go to grocery store, you get it, come back home, you go get it, come back home. So what is happening there? Okay, so that's roughly, that is what it is. Finally, picking up why the iterations are important, why rounds are more important. If you think of, all the items that you're getting from the grocery store roughly have the same weight, and that's not such a big deal, then the number of rounds you make from home to grocery store is what is important. You want to reduce it. Yeah, but the time taken, of course, the time taken will depend upon which car you drive, or what is the road that you are taking, and all that. Okay, so yeah, but in terms of number of iterations per se, you see, let's say your friend is living in a different city, the grocery store may be next door to him, and you are living in a different place, and the grocery store is a bit away from your home, but still the story is the same, right? In terms of, you want to reduce the number of iterations, it still holds good. So while doing this binary search, you need to kind of, the boundary conditions, you have to be a bit more careful. But overall, did you get this idea, the big picture of this, the way we are reduced to go from H to by log H? Are you all with me? Do you feel happy about it? I am excited. It's repetition of the triplets, you see, okay, how to avoid, but this is a nice technique to learn, okay. Let's say repetition, you try to resolve it in a different way, okay. The repetition is not a big problem. Now, when you discover 4, 3, and 5, what do you do? And also, why do you do that in when S1 itself, when you start with S1 is equal to 3 and when you find 4, you stop the story there, right? Why do you want to continue? Why is there a repetition problem? It's not a repetition is not a problem. No? You start with S1 is equal to 3 and you find 4 as the other side, you stop it. So repetition is not a problem here. Okay. Shall we proceed? Think about it, Anika. So think, look at the whole algorithm, think about it. Okay. I will stop. I would like to stop discussion on this and I want to proceed to point out few things in assignment 2. And then what will be the plan for assignment 3 also I want to. This is the best algorithm among the 3. So I would like to point to assignment 3. Assignment 3 is exciting. I want to point what you will be working on in assignment 3. Shall I proceed further? Is it all right with all of you? Okay. Great. Let's look at. So in assignment 2, challenge problem. So how do you, so there is a hotel with 100 floors, 32 rooms on each floor. All the rooms are occupied by single male or female. Okay. How do you store this information? How do you store this information? Yeah. So there are many ways, but the simplest way is, you can have hotel 132 array. Is this okay? And what is the data type of this array, of each element of this array? Int, boolean, char. So let's say if you use int, then how do you represent each? Where if it's a male, 0, if it's female, 1, okay? Or you can use, so if you use, or we can use short int. Can we use short int? Or we can use char also, we can use. And someone said bool, but bool is not a standard data type, but int, short int, char. And then what is the memory occupied? What is the memory occupied if you use? Read about what is short int. 100 into 32 into 4 bytes. Yes or no? And if it is short int, then perhaps on your machine 2 bytes could be allocated into 2 bytes. So if you see among all these presentations, character seems to be the best because it occupies the least amount of memory. Does this make sense? Are you all with me here? Cool. But now the question is, we can even represent, we can even have a very compact representation of it, where we just say int hotel 100. Then what happens is, if you take an integer with 32 bits, we can have bit 0 to bit 31, and bit 0 can represent, if it's male it is 0, and if it is female it is 1, so on and so forth. So we can represent the whole occupancy information in a floor using one integer, 32 bits. Are you all with me here? Does this encoding make sense? An integer contains 32 bits. An integer contains 32 bits. And we take the 0th bit to mean 0th room. First bit is first room. And in the 0th room, if there is a female, we put 0. If it's a male, we put 1, or the other way around, whatever the encoding that we choose. But the problem is, how do we manipulate the bits within an integer? Okay, so here we have to learn what are called as bitwise operators. You go look into Essential C book and it will tell you how there are bitwise operators like AND, OR, exclusive, or negation. Okay, so these things are there in the Essential C book. Okay, I would like you to take a look at it and see how you can use these bitwise operators. Now, I have an important question for you. This is representation 1 and this is representation 2. How much difference in the memory, how much savings you get when you compare representation 1 with representation 2? How much savings of memory you get? 32 times less, 32 times. Not 8 times, 32 times. Here you require 100 times 4 bytes. Here you require 100 times 32 times 4 bytes. when compared with char, okay, yeah, great. But we are talking about R1 and R2. So this representation is very, very important. Why is it important? Because sometimes what happens is the data that you have is too big that it cannot fit into the memory. Excellent, Sarthak. So you could be generous and not care about it, but once you kind of stretch the limits or hit the limits, then you may have to come up with alternate representations so that you will be able to hold all the data in the memory. Okay. Otherwise, you have to store the data on the file system, move the data from the file system to memory, and the complexity of your algorithm increases, your program complexity increases, performance takes a hit, all sorts of issues will come. But if you go to a more compact bit representation, your whole data might fit into the memory and you will be able to get better performance out of your program. Now, if the data doesn't fit, any data which your program has to work upon, it has to be present in the memory. Any data on which your program has to work upon, it has to be present in the memory. So you have to move the data from the file system, from the file to the memory and work on it. If the data doesn't fit into the memory. So what do we do? So there we really have to stretch ourselves and see, can we come up with representation so that the whole data can fit into the memory. Are you with me here? Like for example, let's say if you are working on Wikipedia data will be maybe some 100 terabytes. The 100 terabytes of data. It doesn't fit into memory. So you have to bring parts of the data into memory and work on it, for example. Okay. But on the contrary, if on the contrary, for Wikipedia data, you cannot do anything about it. But there are problems where if you have 32 GB of memory on your system, it could be requiring 40 GB of memory. But if you take a relook at the representation of the data, then perhaps you might be able to squeeze it and store it within 32 GB of memory. And so that you don't need to visit the hard disk at all the computations we can do in the memory. See, I want you to guys to, I'm not interested in exactly solving the problem. I want to use this opportunity to try, to discover different approaches. The representation, there's a bigger thing that is going on here, and that is the one I'm trying to bring it out. Are you with me? I know like you have very clever techniques of doing things, etc. But there's a bigger principle I want to bring out using these techniques, using this problem. So that's the reason I am delving into this. Are you all with me here? This example, how exactly you do the bitwise operations, you will see. Okay, there is one video from the past year I can just show, or I can discuss, or you can read the book. All these things are possible. But the crux of the story is you choose a different representation. The whole, the memory requirement, you are getting 32 times savings or 8 times savings as you see it. Now I have a different question. If each room has a male, female, or it could be empty, will this trick work? Then what do we do? What do we do? So the first case is, it's easy enough. So it is 0 and 1. 0 means male, 1 means female. So now we have to use 2 bits for each row. So 0, 0, 0, 1, 1, 0, 1, 1. This is male, female, empty, and one representation goes waste. Okay. Do you see the encoding here? These are all 4 positive. ZZ, one doesn't mean anything here. You can possibly, if you are, you can possibly, like in a particular hotel, this 11 means the room is reserved for VIPs or something like that. It could encode that. Otherwise, it's just garbage. Okay, so now if you're all good here, can I take 4 more minutes and finish this lecture on giving a preview on assignment 3? Or you're tired? Stop or go or? Just 5 minutes. I want to give a preview for lecture for assignment 3. And then we will stop. Okay. So let's do one thing. So this is okay. So now in assignment 1, what we did is we did the matrix vector dot product of 2 vectors. This is what we did. Now in assignment 2, we will do matrix times vector. So if you have a matrix, m by n matrix, and you have an n by 1 vector, and so you have row 1, you have row 2. So now the matrix vector multiplication, this is column. So what you get is an m by 1 vector. Can you tell me what are the entries of the matrix? This is the first entry is the dot product of row 1 with the column vector C. Yes or no? First element of the, and then similarly R2 times C, R3 times C, so on and so forth. So your matrix vector multiplication is an extension of the dot product problem which you did in assignment 1. This is one problem you will get. And then if you look at matrix multiplication, so this is another thing which you will see. This is m by n, n by o matrix. This is m by o. So here you look at the first matrix as a sequence of rows, and the second matrix, if you look at them as columns, collection of columns. Is it okay to look at the second matrix as a collection of columns? No problem, right? Yeah. Then what will be the first column of the product matrix? The first column of the product matrix is R1 times C1, R2 times C2. So essentially this comes here. And the second column is nothing but R1 times C2, R2 times, no, this is C1 only, sorry. This is C2, yeah, I'm sorry. So the first column here is, the first column of the product matrix is dependent on the first column of the matrix B, and the second column of the product matrix is dependent on the second column of the matrix B, so on and so forth. So you should look at matrix multiplication as an extension of matrix vector multiplication and solve the problem. Are you all with me here? This is not 0, guys. N by O, I think. Okay, sorry. Bad notation. So this particular view will make it easy for you to write the program. That's the reason I'm bringing this up for you. Okay. And now I will show you one more thing. Now comes the real. So the problems that you have seen so far, they are, yeah, let's see. They are the first set of problems, and we will see the second set of problems. The second set of problems, like for quadratic equations, if it's a quadratic equation, you have a closed form formula to solve to find the roots of a quadratic equation, right? Okay, minus b plus of minus b square minus whatever, blah. Okay, so this is one problem you will solve. And then there are other techniques which are used to find roots of equation functions. So you will write programs for them. We exclude this one. The other methods we will do. This is the second set of problems we will solve. And the third set of problems you will be solving is Gaussian elimination method. When we have systems of linear equations, how do we go about solving them? That is the third set of problems. The first set of problems, matrix vector multiplication, matrix multiplication, basic. Second set of problems is on how do we find roots using different algorithms. And the third set of problems is on how do we solve systems of linear equations. I will post these questions. I will post these problems by today, tomorrow maybe, and you will get 2 weeks to solve these problems. These are very, very interesting problems. Very, very nice problems, guys. You'll enjoy it. Okay. If you solve these problems, you feel on the top of the world. Okay. And I want you to feel to be on the top of the world. Okay. So So, all right then. So I think I will stop. I'm sorry I took a bit more time because I got carried away with that binary search thing. It's a nice. I didn't plan for it before, but then I saw the suggestion. I thought let's do it. So short, like 20 minutes. So yeah, I will share the recordings of the previous lecture, but for the next couple of weeks, stay focused. These problems are interesting. Enjoy them. Don't get scared. Discuss algorithms with your friends. Understand them, but don't copy code. You are allowed to discuss, but don't copy code. Okay. All good. So.